All right. So I wanted to, based on the questions that I was getting and on the emails or stuff that was going on last week, um, I wanted to make sure everybody really understands what's going on with this whole Fourier series concept and Fourier transform concept. So wanted to go through sort of a quick example here at the beginning. Okay. So this was a problem in homework 7. This was, I think, problem 3, right? So this guy is a periodic waveform. And I say he's periodic. Why? What makes this thing periodic? What's my definition of periodic?
It repeats.
Repeats, right? And so the definition we say is x of t equals x of t plus capital T. In other words, the value that I have now is equal to the value I have a period later. Okay, so we have that basic relationship. So here's this periodic waveform, repeats on both sides, and essentially it is a sum of sinusoids. We can represent any periodic waveform, so with any one of these 3 representations of what I call the Fourier series. Okay, either it's cosine and sine directly, or it's a cosine, or it's some combination of complex exponentials. So let me ask you this, all right? So if, and maybe let me make one more point, I guess, first, right? So before I ask you that question, I say that all of these sinusoids are harmonically related to each other. What does that mean for them to be harmonically related?
Their wavelengths are integer multiples of each other?
Their frequencies are integer multiples of each
Oh,
other. Okay,
right.
so yeah, frequency and wavelength are a little bit different. So I always kind of, wavelength's more of a physics thing, right? So when you're talking about physical distance of waves, when you're talking about that, we're always talking about things as a function of time. But you're right, their frequencies are functions, or their frequencies are integer multiples of each other, right? So if I had n equals, we talk about the different values. I usually call my fundamental frequency omega naught. Okay, what harmonic has the frequency omega naught? Which number harmonic has the fundamental frequency?
The first one?
The first one, right? So for n equal to 1, the frequency I have is omega naught. All right. The n equal to 0 means what frequency?
0.
Yeah, DC. Okay. And then if I have 2, it means 2 omega naught. Okay. If it's 3, it's 3 omega naught. Okay. So we call those things, so the signal that goes with that, all right, the signal that goes with that, which is essentially either this shifted cosine, this sine plus cosine, is what we call the harmonic, right? The actual so if I say the first harmonic, what I'm referring to really is to say, well, I mean, it's the C1 cosine omega naught t plus theta 1. All right. Now, why does this series, the one down here, the complex form, that's the one I make you use to do the math most of the time. Why does that one go from negative infinity to positive infinity, but this one goes from 1 to infinity? And this one. Why does this one, the complex, go from negative to positive infinity?
Well, because each cosine.
Go for it.
Each cosine is like the sum of a positive and a negative part.
Yes. Right. So, just to reiterate that, to make sure that we're clear on this, we talked about this before, but basically, the difference is, in this case, let's say this guy right here, all right, is alpha 1 e to the j omega naught t. And this guy right here is alpha minus 1 e to the negative j omega naught t. I have drawn these in the real imaginary plane, the complex plane. These are vectors, okay? These guys are vectors. And the one with the frequency omega naught rotates in the positive direction, so the counterclockwise direction. And the one with the negative frequency rotates in the the clockwise direction. So this guy is, just to be clear, this one is clockwise. And this guy is counterclockwise. All right, this is positive, this is negative. What do we know about the sum of those two vectors? If you just look at those two vectors, forgetting anything about Euler's identity or any of that sort of stuff, right? If I just showed you the picture that you have on the left, what do you know has to be true about the sum of those two vectors?
It'll just be purely horizontal.
It'd be purely horizontal. And what about the length of it?
The length will be just like the real part of.
Well,
the
yeah,
vectors.
it'll be twice the real part of any one of these guys, right? Right, their imaginary part, one has an imaginary part up, one has an imaginary part down by the same amount, so they cancel each other. All right, and if they rotate at the same rate, then their imaginary parts are always going to cancel each other. Okay, and so it's an entirely real vector. And if I watched as time advanced, what would happen to this vector as time advances? So the summation, what would happen to that summation?
It would start decreasing, right, until it goes to 0. Then it would go to the negatives.
Yep, it would decrease until it gets to 0, and then it would start going negative. And if I just looked at the magnitude of this vector over time, as time advances, it would trace out cosine. All right, that's the basic idea of this thing. It just so happens that the math, even if you disagree with me, the math gets a lot simpler. If you were doing the integration by parts that you're doing on the homework right now with cosine and sine, you'd have two integrals to do if it was cosine and sine. You'd have a lot, and the integration by parts is a lot worse. So we tend to use this e to the j omega naught t piece because it makes the math a little bit simpler. All right, but potentially makes your understanding a little bit more challenging, right? So I just want to make sure that you guys sort of follow the idea. All right, so when I look at these series, the idea of these series is I can take a sum of sines and cosines and create any periodic waveform. Our job, when you guys are doing those integrals, your job is to basically find out how much of each of those sine waves and cosine waves I need to be able to add up to the original waveform. All right, that's what those integrals are computing. How much? What's the amplitude of those sines and cosines that I need to add in there? Okay, so this was a picture I drew at the very beginning when we first started talking about Fourier series, and I wanted to go back to it a little bit to make sure that you guys, got the picture, because I was getting, a lot of questions, particularly about problem 3 and 4 in the current homework. What this series basically means is if I have a periodic waveform, so in this case, I just gave you what this periodic waveform is here, right? So I'm looking at this guy by inspection. And what I do is I think of each of these amplitudes, A0, A1, B1, A2, so on and so forth. In my mind, they're sort of knobs. How much do I need to turn the knob on the cosine component at the fundamental to be able to get to the true waveform as it's represented, right? So we did this all the way back at the beginning, right? So what this says is, if looking at this waveform, the fundamental frequency is 10 radians per second, it says that I need this A1 value to be 10, and I need this B1 value to be 0. And then how much A2 and B2 do I need for this waveform? So for the one I have circled down here, how much A2 and B2 do I need?
0.
0 for each. Yep. Because there is no second harmonic. So to say that there is no second harmonic means that you want to zero out the sinusoid and cosinusoid that have twice the frequency as the fundamental. But I do need some A3.
Wouldn't A1 be 3?
Oh, sorry, A1 would be 3. Sorry, I was looking at the frequency when I wrote that. A1 would be
Okay.
3. Thank you. All right, A1 would be 3. Now, if I wanted to figure out A3 and B3, you guys should know that they're there, but A3 is not 4, right? A3 is not this. You don't look at that and say I have a cosine. I need to go back to the trig identities and say, well, 4 cosine 30t plus 30 degrees would be equal to 4 cosine 30 degrees cosine 30t minus 4 sine 30 degrees sine 30t. And so this guy would be 4 cosine 30, and this guy would be negative 4 sine 30. Okay, and that just comes straight from a trig identity. So basically what we're doing is we're trying to figure out how much of each of those, I called these guys sometimes a basis, right? These are the sort of the fundamental building blocks. And I need to figure out how much of each of those building blocks I need to put in there to be able to create the original waveform. Okay. Now you will see you'll probably see this revisited a little bit, a question like this on exam 3. All right. Because I think you guys are still struggling a little bit to understand the concept, and I think it's an important one for you to grasp. Okay. Any questions about this before I move on? Okay. And you can always ask questions later if you're afraid to ask them now. All right. So back to this original signal I started with at the very beginning, right? The question you're answering when you get the alpha n values is you're trying to figure out what amplitudes and angles do I need to recreate this waveform. So you're figuring out, you know that this guy has cosines and sines in it. You're trying to figure out the amplitudes of each of those cosines and sines. All right. So what I wanted to do is I wanted to show, okay, well, let's say I did the integral here. So I went through and I did this integral. So alpha n equals 1 over 10. And I did the integral 0 to 10 of x of t e to the negative j omega naught n t dt. And so you would have to go and figure out what the x of t values are, and you would get your alpha n's, and then you would put some code together to basically plot this thing. All right. So I wanted to kind of look at this because what you're ultimately doing at the end of the day is you are basically saying that the function requires how many sine waves, and looking at that and looking at this definition here, how many sine waves does it take to get to this thing? How many harmonics do I need? Infinite, right? And of course I can't have the computer do infinite. It's not going to work, right? So when we do it, when you guys plot them, you're plotting approximations. You're including some of the harmonics, but not all of them. And I've generally been asking you to do up to like 100, because at that point you should have enough that it should look pretty much like the original waveform, okay? So I wanted to play this out a little bit and say, well, x of t is really equal to the sum from n equal minus infinity to infinity, alpha n e to the j n omega naught t. And I say, well, that's what it really is, but let me approximate it first as alpha naught. All right, so in other words, I'm not putting in any of those sinusoids. Okay, and to do that, what I did here was I created a piece of code where I ran my for loop for one iteration. Okay, so from 1 to 1 to 1, so it basically iterated once. And to do that, basically what I get is a DC value. So for that particular waveform, what I got was the DC value was 0.2. So that is with the 0, this is the 0th harmonic. What it says is I need 0.2 to get the DC value of that waveform properly represented. So now I want to include the first harmonic. So if I add the first harmonic to this, what's it going to look like once I add the first harmonic in? What will I be seeing then?
It'll just be like a shifted sine wave.
Yep,
Yeah,
that's right. That's what it looks like right there. All right, so what I did was I said, well, again, remember, x of t is not what I wrote there. X of t is approximately what I wrote there. X of t is the summation n equal minus infinity to infinity, alpha n e to the j n omega naught t, like that. All right, but so what I've done is I said, well, let's just do up to the first harmonic. So that means I got alpha 1 and alpha minus 1 there. Okay, so I have 2 of these rotating vectors, which means I have 1 cosine. All right. And I've written C1 here. C1, how does C1 relate to the alpha 1 value? If I've written it like that. Anybody remember? How does this, go ahead.
Isn't it like double?
Yeah,
of-
that's right.
Yeah.
It is. C1 is equal to 2 times the magnitude of alpha 1. All right, now I'm going to include the second harmonic. If I include the second harmonic, what does that look to? What's the second harmonic going to do?
Well, our approximation is going to get closer.
It's going to get closer, right? And I'm going to add, to get it closer, I'm going to add in a term that has twice the frequency, right? So in this case, what I've got here is I've added two terms, all right, into the complex form, and I've added a single cosine at twice the frequency. All right, now notice it's shifted a little bit, so its angle must be kind of funny, but notice this picture here is getting a little bit closer to that picture. All right, and it's including two harmonics, and it's saying I probably needed less of the second harmonic signal than I did of the first. And as time goes on, I'm going to need probably less and less and less of each of the later harmonics. So if I include the third, now I have three cosine waves, right? So that means that I have, in terms of the harmonics here, I have two terms in the complex series for the first harmonic, two terms for the second, two terms for the third. All right, and each of those equals a single cosine with a different frequency. Okay. Now, it looks a little bit better now in terms of the picture. And then basically I finally did up to 10. All right. So once I did up to 10, you can see that it's really starting to look like that now. All right. And so it's starting to finally have the shape that I would sort of expect it to. All right. Now, we don't just do this just to do this, right? There is a reason for doing it, which we're going to start looking at today, which is to say that, you know, oftentimes you might take a signal like this one that I showed at the very beginning, and you might put it through a circuit. And as a result of putting it through a circuit, it's going to get quote unquote filtered. All right. And we're going to look at that concept a little bit today. All right. It's the last concept that we're going to look at in this class. All right. So before I move on with that, I wanted to just maybe stop. You guys get the idea of what's going on there? Because this is in homework 8, particularly in problem 4, I think it is, the last problem. I ask you to plot the first and the 9th harmonic, which means that I'm asking you to plot the cosine that has a frequency omega naught and the cosine that has a frequency of 9 omega naught. I'm asking you to plot those two waveforms on and to give me those, because I want to make sure that you understand that idea. All right. Now, this is something we've talked about quite a bit at this point, but I just stop here for a second, see if you guys have any questions at all before I move on.
Yeah, I understand this part. So I had just maybe kind of an unrelated question, but it related to something you said earlier when you're talking about you chose 100 harmonics.
Yep.
Just because that's a good number. Why in the last couple homeworks did you choose, just out of curiosity, the t vector, like the period over 10,000 instead of 1,000? Why did we make that change?
That's a great question. When it comes to choosing the time vector, one of the key things about thinking about the time vector, this goes back to project 1, right? I want to make sure that the steps, the individual steps in my time vector are small enough that I can accurately represent the waveform. And by the time I'm at a signal that has 100 times the fundamental frequency, it has 1/100th of the period. And so what I did was trying to make sure that I had 100 times, my time step was 100 times smaller than the smallest period I had. You follow that too?
Yeah, I do follow that. Yeah.
Okay. Yeah, I mean, to some extent, it's a little bit arbitrary, right? I just know that's sufficient to be able to see it.
Okay. So what would happen? Would it be less accurate if I just out of curiosity switch that to like 1,000 or 100?
It probably wouldn't be that less accurate. I mean, 100 it might be. And the reason for that is something I'll actually touch on here in a second, right? Which is to say that as the harmonic number gets higher and higher and higher, the importance of that harmonic grows smaller and smaller and smaller. If you think about it, like what this is saying is, like by the time I've included 10 harmonics, that guy looks pretty similar to my original waveform. But the what I would call the higher frequency content kind of fills in the details. Like if you look at this guy looks a little bit more rounded maybe than he should, right? And so, but otherwise his basic shape looks the same. So sometimes the way I think about this, the higher harmonics are basically the fine details, if you will. So they don't contain a lot of quote information in my mind. They contain maybe some important information to make this guy look just right, but they're just details. They're not all that significant for getting the basic idea of the waveform down. So because of the fact that they don't carry quote as much information, they're not as important to get right, let's say. Does that make sense?
Maybe, and you correct me if I'm wrong, if this is not a right way to think about it, but the more harmonics we have, the closer it's getting to what you might say like an ideal signal.
That is correct. That is entirely correct. Yeah. You said that really well, right? Is I need enough harmonics to be able to accurately represent it, but I don't need all of them necessarily to accurately represent it.
Can I see the integral for the alphas one more time?
It's that.
Okay, thank you.
Now, before you do that integral, the first thing you got to do is you got to figure out, well, what does x of t look like over a period, right? And
yeah,
I haven't done that here. I haven't said what that is, but you'd have to figure that out. So in this case, you would have ultimately 3 different sections to look at. I'd have this section. So 1, 2, 3, 4. Which one of these is irrelevant, this one. Right, but you'd have 3 sections to look at. But you'd have to get the function right over each of those sections.
right. And then you just treat x of t as like a constant, right?
No, you would treat x of t as a function, right? So if you look at this case, and I'll do this real quick just to make sure we got it, right? X of t would be just the function t from 0 to t to 1 like that, right? He's just rising linearly. Then he would be 1 from 1 to 2. Now, I think the thing that causes you guys problems is what does it look like from 2 to 3?
Yeah, I think for me personally, I just overthought that until I really looked at it.
It's the equation of a line, right? So I know that it's x equals, I'll write it as mt plus b. All right, so the slope of that should be, hopefully you guys see the slope of that's what?
-1.
-1, right? So it's minus t plus b. Then I got to figure out what b is, the actual offset. I think a lot of people tried to put in minus t. That's not minus t. That's minus t plus b. And I got to say, well, so x equals 0 when t equals 3. So minus 3 plus b says that the offset of that guy is 3. So this guy would be 3 minus t from 2 to 3. And he's going to be 0 from 3 to 10. Like that. And those are the 3 integrals I'd have to do. Or technically 4 integrals, but only 3 of them require work. All right.
And just to clarify, we can take this integral over one period because the signal's periodic and it repeats. We just have to take one period.
Yeah, you just have to do it over one period. You can do it over any period, doesn't matter which one, right? You could do it from 10 to 20 and you would get the same answer, right? That's the important thing. Whatever I choose, I would get the same answer.
So would the first integral you do be from 0 to 1, then 1 to 2, then 2 to 3, and then the rest would just be 0?
Yep.
Okay, cool. That makes sense.
So you just break them up like that. And again, it doesn't matter what period you use. You can use any period you want. All right, you could go from 10 to 20. You could go from 100 to 110. The only thing happens with that is you have, for whatever period you choose, your functions would be different here, right? If you chose from 10 to 20, you would need to figure out, well, what's the function for this line? I don't know what that is, but it's probably it's gonna have a slope of t, but its offset's gonna be different. All right, you can figure out what that offset's gonna be. All right. All right, so I wanted to make sure that concept was understood. Now I want to real quick, okay, this thing with the Fourier transform. So we talked about this. The Fourier transform basically says, all right, at what frequencies are there sinusoids and how much sinusoid do I have at those frequencies? So the Fourier transform guy, what he is he's a plot versus frequency. All right, so it shows, notice so if I got a little x here for my waveform, I got a capital X for my Fourier transform. All right, and so what this guy is he's a series of impulses, and there's only impulses at those points where there is a sinusoid. The term I use is where there's, quote, information in the signal. All right, and we're going to look at an example of this here. Actually, maybe I'll just jump to an example now, right? So I have set up something I did way back at the beginning of the semester, so I basically was showing you guys, so I've got a radio hooked up to my computer, and this is a program going into that radio, and I'm going to run this thing right here. Before I run it though, this thing I have right here, this guy, it says WX GUI FFT sync. This guy is computing a Fourier transform, and it's an FM radio that I've made. Okay, so if you have FM radio, what kind of frequencies is FM radio? What are the frequency numbers for FM? Nobody listens to the radio anymore, probably.
It's like megahertz, right?
Yeah, it's around 100 megahertz or so. Usually, I think it's between like 90 and about 108. Okay, so if I run this, take a second for it to start. All right, here's that FFT. All right, what it's showing me is what? All right, so, and I can, if I want to hear it, I don't think it likes me. This is a GNU radio, they call this. So I think this guy's sort of an open source program, so I wouldn't be surprised if he gets a little bit hosed up on me here. All right, I'm prepared for this though. I've got a screenshot of it. All right, so here's a screenshot of that same thing. What is this telling me here? What is this picture telling me? No, you don't know what the units are here. It says power in dB. Forget that unit, right, for a second. So notice the x-axis says I got frequencies in megahertz, right? What is this telling me here? What do you think? Go ahead.
The spikes, I mean, the frequencies that we would want would be the ones with the highest.
Yeah. The frequencies the frequencies where I have spikes mean that there is a sine wave at that frequency coming in on the antenna, is what that means. All right, so if I look here, this guy's right now sort of centered around 104 megahertz. And I can see I've got radio stations around there. So if you know the radio stations in Charlotte, there should be some radio stations in that range. So basically, wherever I have one of these spikes, I have a radio station. And if the spike is bigger, what do you think that means? If the spike is bigger?
Signal's more powerful.
Signal, yeah, basically it has a bigger amplitude at my antenna, right? Which means that it's, quote, more powerful, right? So it means that I'm probably closer to that radio station. And so I'm receiving that guy. So let's see if he's still, yeah, he's still hosed up there. So I don't know what's going on with that, but essentially what this tells me is wherever I have spikes, those are the amplitudes of sine waves that I have in my waveform. And try it one more time, see if it'll work. All right, so I can turn up the volume a little bit. And you can see the amplitudes kind of change a little bit over time. This guy's kind of dancing around. He really doesn't want me to do this. Hopefully he won't. There we go. All right. Anyway, you guys get the idea, right, of what's going on with this particular waveform. So this idea of a Fourier transform is really to tell me where do I have signals that are coming in. So it gives me a nice, easy way to see that. Now, if I have periodic waveforms, then everything is closely related to the Fourier series. Okay. So again, if I have something like this guy right here, so 4 plus cosine, or 4 plus 3 cosine omega naught t minus 30 degrees. What I did was I broke that down using Euler's identity into this guy. So notice if I had 1 cosine at omega naught, that means I have 1 vector moving in the positive direction at the same rate and 1 vector moving in the negative direction at the same rate. So looking at that guy, what are my alpha naught, alpha 1, and alpha minus 1? What are those? For that particular waveform, what are these numbers?
So you have your amplitudes for DC.
Yeah, so what's my alpha 0 term?
The alpha 0 term would be
It'd be 8, right?
8.
It would be 4.
Yeah, it's 4. 8.
Yeah,
8 is the
one of the things,
speed.
again, yeah, it's really, again, they didn't let me define this. I wouldn't have defined it this way, right? If you look at this guy, he is always going to have, there's no over 2 that goes on with that. The alpha 0 term is the DC value, and in the other 2 forms of the series, there's that over 2. And I could talk about why that was done, but it's not all that important. But it is what it is. But alpha naught is 4. The DC term is 4. All right, now what about alpha 1? What would that guy be?
1.5.
Not 1.5. Close. 1.5 times what?
Oh, 2.
Nope.
Times
Oh.
e to the j 30.
E to the j negative 30, right?
30.
Right. If you don't want to write
Yeah.
that in complex exponential form, you could say he's a phasor with a negative 30 degree angle. This guy has a 30 degree angle. All right. And the reason why, you can go back to Euler's identity to figure out why the negative goes with the positive moving vector and why the positive angle goes with the negative moving vector. That just comes from Euler's identity, which is a cosine of theta equals a over 2 times e to the j theta plus e to the minus j theta, like that. All right. And you would see where that comes from there. Now, what does that mean then in terms of this Fourier transform idea? If I drew the Fourier transform, and again, the Fourier transform is tricky because each of these terms, alpha 0, alpha 1, and alpha minus 1, those are complex. So I can't draw the Fourier transform, right? I can't draw a complex waveform versus omega, right? In other words, x is a function of omega, but x is complex, meaning it has a magnitude and an angle. Like that. So I have to draw the magnitude and angle separately. Okay, so what would I be drawing here? What would I draw for the magnitude?
The impulse.
Okay, where would I have impulses? How many impulses would I have and where would they be?
In this case, you would have 3. Alpha naught would be at the origin, but going up to 4.
Yep.
And then you'd have a 1 at 1.5.
Yep.
But going, yeah. Well, I guess my question is, why wouldn't it be going down if it's negative 30?
Because that's the angle. Right?
Okay.
The magnitude's always a positive number, and its location is omega naught and negative omega naught.
Got it. Okay.
Okay. Now, somebody other than Anthony, help me out with the angle. What would I say for the angle here? So there's impulses again at omega naught and at negative omega naught. All right. At omega naught, what do I label that impulse as?
Minus 30.
Minus 30. So this guy's going to go down to minus 30. And this guy at negative omega naught would go up to 30. Now, if you notice the picture I showed here, this is just the amplitude. Again, we'll talk about this unit next week, this dB unit. It's basically the log of the amplitude, and there's a reason we do that. No one ever usually looks at the angle. All right, no one ever usually looks at the angle. Occasionally you need it, and in controls, that's a place where it's sometimes used. But for the most part, we don't talk about it all that much. All right, but you guys follow what I did here to map this signal to its Fourier transform? Any questions about that? All right. If I wanted to write it in terms of those impulses, I would say, well, this guy becomes 4 delta of omega plus 1.5 e to the negative j 30 degrees located at omega minus omega naught, right? This is the term at omega equal to omega naught plus 1.5 e to the j 30 degrees at omega plus omega naught, right? This last one is the term at omega equal to negative omega naught. All right, it matters to know, to be able to do the shifts that you need to do to locate these impulses properly. You guys follow how to locate those impulses properly?
And that's just by, I guess, by design for omega naught to be, in the first case, a negative degree, we have a positive omega naught, as well as the
Well,
inverse.
think about it like this. If I tell you delta of omega minus omega naught, if I plug in omega equal to omega naught into that, what's this become?
Okay, I see.
It becomes 0, right?
Yeah,
In
0,
other
yeah.
words, at omega naught, this guy looks like
Okay, yeah.
the impulse here. That's what that means.
Okay.
All right. That's how we shift waveforms around in general. Right. So if I have a negative, so if I have x of t minus 2, then I take x of t and shift it to the right. If I have x of t plus 2, right, I shift that to the left. All right. That's the idea. So I talked about this last time, and there's 2 sub videos that I uploaded from last Thursday's lecture that goes through one sort of what I call a simpler example like this one, and then one that's also based on just a more general periodic waveform. And the steps, basically, you got to get the Fourier series coefficients, you got to get them to the right frequencies, and then you got to determine x of omega as a set of impulses at the right spots. All right, so I did this here. I plotted it 2 different ways. So I did this for this waveform. All right, so for this guy right here, I basically I did the Fourier transform of that thing. So if you notice, I plotted it 2 different ways, right? I plotted it just so you guys could understand a little bit more easily. Is I always have 2 plots, right? One is the magnitude, one is the angle. This one here is plotted versus omega. This one here I plotted versus n. So you could kind of see what the relationship is, right? N equal to 0 relates to omega equal to 0. N equal to 1 relates to omega naught. Okay. N equal to 2 relates to 2 omega naught. All right. And so on and so forth. But what I can see from this, and the reason that I wanted to look at it this way, is one thing we just talked about here is if I look at how these guys flow over time, what do you notice as the harmonic number gets bigger and bigger? So in other words, by the time I get to n equal to 10, or 10 times omega naught, what do you notice about the magnitudes there?
Goes to 0.
Yeah, they start to get small. Whether it's 0 or not, I don't know, but they definitely start to get small. And that kind of goes with the questions that that I think Tim was asking earlier, which is that, you know, the higher frequency harmonics tend to matter less and less. They're important for the quote details, if you will, right? Think about building a house, right? I get the house all built by putting up the studs and making sure the drywall's in place and all that. and that's a house, it's functional, right? But I want to put up, some, molding and stuff like that. There's some details that I put in, which are maybe not as they're not critical to having a house, right? But they're critical to making the house look nice. And that's kind of the same concept, is that these higher frequency guys give us the details to make things look nicer, if you will. All right, it's kind of a way to think about it, maybe. All right, questions about that? All right. All right, I'm gonna move on to think about how we use this stuff, because at the end of the day, that's what matters, right? It's not just that we know how to compute them, but that we know what to do with them. And there's real things that we use this stuff a lot. That's why I used that radio example there, right? Because this is used all the time for analyzing different types of things in the real world. Now, one thing, I'm not going to talk about this at all, but the Fourier transform is more general. All the things that I've given you are periodic waveforms. If I have periodic waveforms, then what I get are impulses. All right, so over here, I'm going to introduce this term frequency domain in a second, but this is basically my Fourier transform. If I have a single sine wave, I get a single impulse as my Fourier transform. If I have a square wave, I get all these harmonics that come into play. All right. But I can have other more complicated waveforms. Like this guy, it says damped transient. Well, this guy is basically e to the negative something t cosine omega dt. That's not a pure cosine now, right? This guy has a more complicated thing. All right. Basically, if I have a waveform that's not periodic, which most waveforms in the world are not periodic, right? Then I get a more complicated Fourier transform. You will talk about that in signals and systems. All right. I wanted to introduce the idea here, but we won't have anything complicated like that. Okay. All right. So I want to talk a little bit about where I would use this thing. And so I'm going to flip over to my other presentation here. So this is an idea that some of you guys have probably worked with before at some point, maybe even in 1202. But this is what I would say if I had a robotics type of problem. If I was trying to drive a motor, all right. So in robotics, we often talk about DC motors. Okay. Here's a question. So what kind of voltage do you apply to a DC motor, do you think? Trick question.
DC voltage.
That's a good guess. That is in the old school way of doing things. That's what I would do. I would put a DC voltage on a DC motor, and without going through the physics of a DC motor, if I put 0 volts on a DC motor, how fast do you think it goes? Doesn't go at all, right? It doesn't move. If I put 5 volts on a DC motor, it'll start moving. If I put 10 volts on a DC motor, what do you think is going to happen to its speed?
It'll double.
It'll approximately double, right? By the theories of physics, if I keep doubling the voltage, I'll double the speed, okay? How in the real world, like let's say you're gonna make a car, and that car was going to have a DC motor. Now, a real car, if I looked at an electric vehicle, you would never, ever, ever have a DC motor. You would have an AC motor, okay? But let's just say you did. Let's say you had a DC motor in a car. How would you create a controllable voltage source to drive that motor? What would be one way to create a controllable voltage source for a DC motor?
I guess like a regulator potentiometer.
Okay, potentiometer is a great. So what is a potentiometer?
Well, that helps you control like how much voltage is being pushed.
Well, what is a potentiometer?
It's a resistor, isn't it?
Yeah, it's
Yeah.
a resistor. Basically, I have a resistor that I can vary its resistance from 0 to some value. And so here's my motor. All right. So if I turn the potentiometer, then I can change the voltage I apply to the motor. And this would be my battery. So let's say my battery was 12 volts. Okay. I could basically turn that guy. This is never ever done in practice, but it works. Very simple. Why would you never do that? Any ideas?
Isn't
I
it like
mean,
inefficient?
What's that?
Like isn't isn't it like more so inefficient and that's why it's not used in
Yeah.
practice?
That's great. Yeah, that's a perfect answer. It's incredibly inefficient because some of the power that leaves this 12-volt source basically enters that resistor and it gets wasted. All right, it's a very inefficient way of doing it. But somebody figured out that I could basically utilize Fourier to do it with near 100% efficiency. And to do that, if you've ever played around with some robotics stuff, and you may have done this in your embedded systems class or maybe in 1202, is this guy? This is an Arduino here. All right, so you can look this up online. So I have an Arduino, and this is an Arduino motor shield, is what it's called. What that guy does is he puts a voltage onto the DC motor that looks like this. All right. Anybody know what kind of waveform, what I call that? It's kind of square wavy, but it has a particular name. Anybody know what the name of that is?
Something like a pulse width
Yep.
modulation or
Yep,
something?
it's a pulse width modulated waveform. It's a PWM wave. Right. So what we do is it's a square wave, has a fixed frequency. And what I do is I vary the width of this pulse. Okay. And this is written kind of crappily here, but this is the letter D. That D is the fraction of a period from 0 to 1. And what I do is I change the width of this guy. I change D to make this guy wider or narrower. All right. So in the context of Fourier series, right? What's happening to the what's the DC component? What frequency is the DC component?
0.
0. All right. And how did I compute that component? How did I compute the DC component? Wasn't that guy computed a little bit differently? We did this, right? Oh, whoa, what did I do? 1 over t, 0 to t, x of t, dt. This guy's a little bit different. He doesn't have that e to the negative j omega naught t stuff going on. What do we call that? This guy's alpha 0. The DC
average.
term. The average, right? So if I make this pulse, if I make this width wider, what's going to happen to that DC value?
It's gonna be bigger.
It's going to be bigger. All right. If I make it more narrow, the DC, the average value is going to get smaller, right? Because the area under the curve here is going to get bigger if I make this pulse get bigger. Now, what I wanted to do is I want to kind of motivate this idea a little bit because, all right, so this guy has a DC value, right? But he also has what? I mean, if this guy is periodic, then technically that voltage that I'm applying to the motor has a DC term plus what else? What else has to be included? Not just the DC term, but what else? It's a periodic waveform, so any periodic waveform can be expressed as what?
Sines
Sine
Sines and cosines. And how many sines and cosines are in here?
just as
Infinite.
much.
Infinite, right? So what I wanted to do is maybe give a quick example. If I take a motor like this, all right, what I'm going to do is, so here's a motor, all right, and I'm going to apply a voltage to this motor at a low frequency. Now, if I apply so it's going to be a square wave voltage like what I was just showing there, but at a low frequency. So what do you think this, so this is an arm connected to the motor. What do you think is going to happen when I do that? If I apply a low frequency to it?
It would start oscillating slowly.
Yeah, basically what I'm going to see is I'm going to see it go and then stop and then go and then stop. So let me play this. Let me apply the voltage. I have to listen to this guy. All right. All right, so notice what it's doing here. The motor is spinning and stopping and spinning and stopping and spinning and stopping. And there's the voltage on the oscilloscope there. So it spins when the voltage is positive and it stops when the voltage is slow or is 0. All right, does that make sense what's going on? It's a pretty simple idea. Apply voltage, it goes. Don't apply voltage and it doesn't go. Now let me go forward in time here. And what I end up doing is I take the frequency and I move the frequency up to a kilohertz. Now it should be moving continuously, but it's kind of moving continuously. I have noticed those pulse widths are really narrow. I'm going to make them bigger here. So I'm going to change that pulse width. We call it the duty ratio. I turn it up to 90%. All right, now what I see is basically a continuous motion of this thing. All right, there's what the waveform looks like. And I see a continuous motion. What's going on? Why do I see a continuous motion with this, but when it was slower, I saw a discontinuous motion? What's happening?
Well, the motor has some momentum, so it's not like it would stop like moving for 1,000th of a second.
Right. So, oops. So you're right. The motor has some momentum. So what's going on is what?
You expanded that.
Well, so what the motor is doing is it's not responding to these high frequency cosine and sine waves. Whereas it was, when the frequency was low, it was responding to all of those cosine and sine waves. But if I made the frequency get a lot higher, it was only responding now to the DC term. So what the motor was doing is it was, quote, filtering out all of these other terms. So I basically created a waveform that had all these sines and cosines in it. But that momentum you called of the motor, basically the motor was somehow not responding to those higher frequencies. That's an act of filtering. So I think in 2112 right now, you guys may be talking about filters, or at some point you probably talked about filters, right? Have you guys talked about those?
Yeah.
A little bit.
Yeah, so what that motor is it's a low pass filter. I am giving it lots of frequencies, and it's only accepting the DC frequency. It's only responding to the zero frequency, right? And this is a pretty common, phenomenon. Now, this basic idea allows me to create a circuit that's super efficient, way more so than this guy, all right, to be able to control this motor in a really efficient way, because the motor is acting as what I would call a low pass filter and rejecting all of these high frequency harmonics. This idea is pretty commonly used, and it's why if you've ever played with a motor, you always use PWM to drive it because of this idea. So I want to understand that a little bit, but essentially, if I can use Fourier series in an engineering context, what I want to be able to do is to use those concepts with this filtering idea to get a system to do what I want it to do. Like in this case, I got the motor to move continuously in a nice, smooth, efficient way by using this concept. All right. So to do that, I need something for my filters or something for all of my circuits and systems that I call a transfer function.
Professor,
Right? So, yeah.
you stopped sharing your screen. Was that intentional?
No, it was not.
You've been having internet issues like as well. Your voice has been lagging every now and then.
Well, it's not. Okay, it's good to know, but not much I can do about that now. It's probably because I'm at home today as opposed to in the building. All right.
Got that sweet college Wi-Fi.
Yeah. All right. So if we go with this guy here, right? So here is a differential equation that came from some circuit or some system, right? If I have this, and this could represent some sort of a circuit. If I was only interested in getting the steady state component of the output, all right, and this actually relates to something you guys are going to need to go over for the final, which is if I have a cosine omega naught t as my input here, how do I approach this, right? What is the steady state? So this guy's V is the output. What's the steady state or particular solution going to look like? How do we solve that?
Would you just transform it to complex?
I could, and that's what I want to do. right? But in general, I would say this guy is going to be what? He's going to have a different amplitude. Let's say B. What's
Times
the
the
rest?
time step, a unit step.
Well, it would be B
So if I put a
cosine.
cosine, if a cosine is the input, what's the output going to be?
Or cosine.
A cosine. Yeah. And what's his frequency going to be?
The same.
The
Same.
same. His angle might be different. We'll call this phi phi out. I don't know. Phi out. Like that. Okay. And so we don't do it that way. We basically said, well, we'll think of this, we'll think of everything here as this guy is the real part of A e to the j phi e to the j omega t. And this guy is the real part of B e to the j phi out times e to the j omega t. And we just said, let's forget the whole real part thing, and let's just use these guys as essentially we'll just look at the dynamic phasors in here by themselves, okay, and forget the whole real part thing. So if that's the case, the right side of this thing is going to be, let me do it a little farther over. Let's call this guy A e to the j phi e to the j omega t, like that. And over here, I would have A0 times whatever my output is. So this would be B e to the j phi out e to the j omega t. And then I would have all these other terms here. What happens when I have a first derivative? What happens with the first derivative here? What happens when I take the first derivative of this?
So like I guess you would just pull down the j and the omega, right?
Yep. Yeah, I have j omega times B e to the j phi out times e to the j omega t, like that. Now, and I could keep going for all these other terms here, right? If I look at this here, right, what happens to all the e to the j omega t terms?
No.
They all cancel out, right? And what I get here is essentially j omega b e to the j phi out. In fact, I can factor this guy a little bit. J omega, and there was an A1 in front of this guy. So let me put that A1 there. Plus A0 times B e to the j phi out equals A e to the j phi, like that. So what I sometimes do is I can use this relationship now to figure out what B and phi out is. This is two equations, right? It looks like one equation, but there's really two equations here, right? Why are there really two equations there? Why are there really two equations?
The mess of constants times b is equal to a, and j phi out should equal j phi. Right?
Not quite. The angle of the left side equals the angle of the right side. And the magnitude of the left side equals the magnitude of the right side. I think that's what you're trying to say.
Yeah, that was what I was trying to say. Yeah.
Yeah. Right. So there's two equations, one for the magnitude, one for the angle. All right. So what I can do is I can rewrite this guy. I sometimes I'll rewrite this as like this. B e to the j phi out over A e to the j phi is 1 over j omega A1 plus A0, like that. All right. What I did was I rearranged. I basically divided both sides by A e to the j phi, and then divided both sides by this guy. All right. And I got this expression here. What this is sometimes, if I look at this B e to the j phi out, A e to the j phi, actually is kind of if I look at this thing here times e to the j omega t, and this thing here times e to the j omega t, those things are related to Fourier transforms. All right, we're going to go over this more slowly on Tuesday next week. But this guy here looks like it's the Fourier transform of my input. So in this case, Vs of t was my input. This guy is the Fourier transform of my input. B e to the j phi out is the Fourier transform of my output. So I called that V P omega, like that. And this thing right here, this thing is a function of omega. And this thing I call my transfer function.
Yeah, I was literally about to say that.
Yeah, you
Because
heard.
we've been looking at that in network theory too with transfer functions. And when you had like the input and output, that's what it looked like.
Yeah. So, and you can write those transfer functions in different ways. Yahoo might write them as functions of S, maybe. And so where he might say S equals j omega, he might not. I don't know.
Yeah, he does both.
Okay. Yeah. So we have different ways that we sort of express this. But what that thing actually relates, that transfer function relates the Fourier transform of the output to the Fourier transform of the input. All right, and we use that all the time. So what this says is, if I know the input to a system, how does this system, which could be a circuit, how does that system modify the Fourier transform of the input to get to the output? All right. And so Yahoo probably refers to this. He's watching the time here. So that Yahoo probably refers to it like this, where he says, this guy is equal to what I call h of omega. Right, my transfer function. And I can say that the Fourier transform of the output equals the Fourier transform of the transfer function times the Fourier transform of the input. And you've actually been doing this all semester in 2112, right? You're basically using impedances, which result from the Fourier transform. All right, and there's a direct relationship between what you're doing with impedance and the Fourier transform. This viewpoint is sometimes what I refer to as the system's viewpoint. All right, if I have a sinusoidal or cosinusoidal input, I can think of it in this phasor domain, and I can say if I only care about the steady state output, then what I do is I know that the output of this guy in steady state is equal to the input x of t times whatever this transfer function is, right? So this picture that I'm drawing right here basically says, if I can look at my input and I can get my input in the form that I've shown here, I multiply that input by the transfer function, which is given by the circuit or system that I'm looking at. And then I can figure out the output looks like this. So what I did when I showed that thing with the motor there is essentially the motor has some transfer function h of omega, which is basically the output is the speed and the input is the voltage that I apply. So if I know the Fourier transform of this voltage, right, this voltage exists in the time domain, V of t. If I know the Fourier transform of this voltage and I know the transfer function of the motor, then I can figure out what the speed's going to do. All right, this idea is called filtering. When I'm using the transfer function like this, I'm usually designing what I call a quote filter, which basically takes sinusoids at certain frequencies and changes their amplitude and phase. Maybe it makes them go away. If it makes those sinusoids disappear, then I've filtered them out. It might make them get bigger. All right, but this is an idea we're going to explore here in the last part of the semester, and you're going to play with a little bit in the project. Okay. All right, I'm going to cut it there, I guess. Any questions?
I kind of have a question. I'm just wondering if I'm thinking about it right. Is when we're talking about a frequency to initiate the motor, are we talking like an RC car?